Welcome to The Explainer. Today we are pulling back the curtain on a hidden force. It's this, well, invisible power that's behind some of the world's mightiest machines. We're talking about a technology that lifts, digs, and moves with just incredible strength, but it's almost always completely out of sight.
I mean, you've seen it, right? These incredible feats of strength are everywhere. A huge excavator just chewing through solid rock. A car lift raising thousands of pounds like it's nothing. Or, those gigantic wind turbines turning their blades. Have you ever, really stopped to think, what is actually making that happen?
Well, the secret behind all that muscle, it's a technology called fluid power. And you know what? The core idea is actually super simple. You just take a fluid, something like oil or even air, trap it, and then use pressure to transmit power and get some serious work done.
So this all comes down to a discovery from way back by the scientist Blaise Pascal. And the story goes he figured this out with a jug of wine. Get this, he rammed a cork into the full jug, and boom, the whole bottom blew out. So why'd that happen? Well, the pressure inside was equal everywhere. But that same pressure acting on the big area of the bottom created a way bigger force than the little push he put on the cork. And that, right there, is the secret sauce. A small force on a small area turns into a huge force on a larger area.
Okay, so let's get into the nitty-gritty. Fluid power isn't just one thing. It actually comes in two main flavors, you could say. And it all boils down to what kind of fluid you're actually using.
So, on one hand, you have hydraulics, which uses liquids, usually oil. On the other, you have pneumatics, which uses gases, usually just plain old air. And the really crucial difference here, the one thing that changes everything, comes down to a single word: compressibility. See, liquids are incompressible. You can't really squeeze them, but gases, you can compress those. And that one little fact completely changes the game for how each one is used.
Right, so because air is compressible, it has this kind of spongy, springy quality to it. And that makes pneumatic systems fantastic for really fast, repetitive tasks. Think about an assembly line. But if you need to lift something incredibly heavy and hold it perfectly still with absolutely zero give, well, that's when the stiff, rigid, incompressible nature of hydraulics is the undisputed king.
So here's a great way to picture it. Think of hydraulics as the powerful, super precise bodybuilder, lifting massive weights with total control. Then you've got pneumatics, which is more like the quick, nimble sprinter. It's fast, it's cheaper, and it's cleaner too, because it just exhausts air. But it's just not as powerful.
All right, so how does this whole thing actually work? To really get it, let's follow a single drop of hydraulic oil as it makes its way through a really basic system.
A hydraulic circuit is a lot like your own body's circulatory system. Seriously, it's got a heart, a brain, and muscles. So our little drop of oil is going to start its journey right at the heart of the system, which is the pump. Okay, so the pump. Its job is to pull that oil from a tank, the reservoir, and just push it into the system, into the lines. But here's where we run into a really common misconception about what a pump is actually doing.
Most people think the pump's job is to create pressure. But it's not at all. The pump's only job is to create flow. That's it. Pressure only shows up when that flow meets resistance. Think about it. It's the fluid having to push against the weight of a car. That's what creates the pressure. If there's no resistance, there's no pressure, just flow.
Okay, so we've got flow. Our drop of oil is moving through the system, thanks to the pump. But, a constant stream of oil isn't very useful unless you can actually control it, unless you can tell it where to go. And that brings us to the system's brain.
And that's where these things, valves, come into play. They really are the brains of the whole operation. The best way to think of them is like mechanical traffic cops. They're the ones that start, stop, and direct all that fluid flow.
So how does it actually do that?
Well, inside the valve, there's this really precisely machined part called a spool. And when you flip a lever, or an electric signal hits a solenoid, that spool physically shifts inside. It slides over, blocking off one pathway, and at the exact same time, opening up a new one. And just like that, you've redirected this incredibly powerful flow of fluid. It's amazing. A tiny little movement controlling all that immense force.
Okay, so let's recap. Our drop of oil has left the pump, it's been told where to go by a valve, and now it's arriving at its final destination, the part that's going to do the actual work. So how do we get from a moving fluid to actual physical force?
This is where the magic happens. It's in a component called an actuator. This is the muscle of the system. It can be a hydraulic cylinder that pushes and pulls in a straight line, or a hydraulic motor that spins around. This is the part that finally takes all that energy in the fluid and converts it into real mechanical work.
All right, let's circle back to Pascal's law and use a simple hydraulic jack to see it in action. Imagine you push on a small piston with just 10 pounds of your own force, okay? Now let's say that piston has an area of 1 square inch. That means you've just created 10 pounds per square inch, or 10 psi, of pressure in the oil. Now, that same 10 psi is pushing everywhere inside, including on a much bigger piston, say one that's 10 square inches. Well, 10 pounds on every square inch for 10 inches, that creates an incredible 100-pound lifting force.
Just think about that for a second. That's a 10 times multiplication of your force, all from just putting some fluid in a tube and playing with the size of the pistons. But, as you might guess, there's always a catch, right?
Yeah, you never get something for nothing. Here's the trade-off. The price you pay for that huge output force is distance. Your small input piston has to travel a much, much greater distance. So to lift that big piston, say, 1 inch, you might have to pump your little piston 10 inches. So your force gets multiplied, but your movement gets divided. That's the deal.
So now that we have the basic circuit down, you got the pump as the heart, the valve as the brain, and the actuator as the muscle, you're going to start seeing just how common this technology really is.
I mean, the truth is, once you know what to look for, this hidden force is absolutely everywhere. It's in the factory press stamping out car parts. It's in the forklift at your local hardware store, the crane on a construction site. It's what's behind your car's power steering and your brakes. It's even what lowers the landing gear on an airplane, and it's what helps pitch the blades on wind turbines to get the most energy. It's just everywhere.
And it's funny, while the basic ideas are super old, the kind of fluid power we use today really kicked off during the Industrial Revolution. Back then, they used water to power big cranes and presses. But the real game changer, the beginning of the modern era of oil hydraulics, was in 1906. That's when it was first used to aim the giant guns on the battleship USS Virginia. And that just changed everything for both military and industrial tech, forever.
So now you know the secret. The next time you see a garbage truck effortlessly lift a heavy dumpster, or a backhoe digging a trench, or even when you just turn your own car's steering wheel, you'll know what's going on under the surface. You'll spot that hidden force at work, all thanks to the simple but incredibly powerful magic of fluid power. Thanks for joining us for this Explain.